Okay, so let's start by talking about cores. So you might all have heard like multiple cores, quad core processor, something like that. So what does that actually mean? Like, can you use parallelism to run like, let's say Hogwarts Legacy or something? But no, the max that you can do is you can, so there are some problems in astronomy which are called as embarrassingly parallel. So what that means is you have a very simple function that you need to iterate over like need to do the same thing over and over again. So for example, if you have a bits file and you're performing a particular function on that bits file, and you have, let's say, thousands of those bits files. So instead of doing them one after the other, you can set up your system such that all thousand of them will run parallelly. So that's what it means by using multiple cores and using parallelism to solve some of your problems.
Can you make the screen a little bit?
Yeah. Is this better? Okay, thanks. Yeah, but of course, there are caveats when you use parallelism because there is always an overhead of converting your code into a parallel code versus just writing like a Python script, like which calls like 100 different Python scripts. Sometimes that might be easier. And if it does your job, it does your job. Because parallel programming will make your code very complex and it'll be a nightmare to debug. So that's a fair warning for everyone. So if simple Python scripts can do your stuff, you should always go for that. So for this particular lecture, we'll just discuss two main parallelism protocols, and we'll mainly be dealing with Python and threads, pools, processes, and how to use GPUs. So I'll just start by importing anyways. Okay. So you can all follow along. Let me know if you're stuck anywhere, interrupt me anytime, it's all good. So before we go right into the theoretical part, I just wanted to let you have a look into like how a code for a parallel program looks like. So this is a simple function to do something. Also for this lecture, let's not focus into like the math part of stuff. So if you see a math block somewhere, you just see that, okay, it's doing something, but we'll mainly focus on how to parallelize that part. So here we have a function which just finds the brightest spot or something. Yeah. Oh, bigger. Okay. Yeah. Okay.
Yeah.
So the way you do is you create an array of like random integers. So this is just how you initialize your data set. And this is how you create a pool of all the processes. So if you have 4 cores, you can go up to 4 processes. If you have 2 cores, you will use 2 processes. So this you can adjust as per your hardware system requirements are there. So this is how you initialize a pool of worker processes. And then you just map your function and your data set in like a pool.map and save it in result. And every time you use multiprocessing.pool, you need to close the pool and you need to join the pool. So what this does is basically it waits for all the processes to finish doing their tasks, and then it combines the result and then gives you out whatever the result is. So for example, if you want to see, you can just run this part, and yeah, it's super fast. So because it's using like multiple. So that's how a basic multiprocessing code block looks like in general. So now, what exactly is multi-threading and what exactly is multiprocessing? So having multiple threads, so you have multiple cores. Each core will spawn multiple threads. So these can be thought of as very small processes that happen within a single core. So they all share the same memory. Whereas processes happens on different cores. So they will not have access to like a shared memory. So that's the main difference. So you can use a whole core for a single process, or all threads work on the same process. And GPUs are basically multiple lightweight kind of CPUs, and they are like insanely fast. So, but the CUDA and everything is like a nightmare to handle. So it's a bit dicey. And this, for example, is like a supercomputer which you use. It is like an HP one. And as I was prefacing earlier, you can always learn like amazing techniques like CUDA, worker call, CPU, GPU. But always remember that if you can get the job done by using just multiple Python scripts, you should go for that. If the time difference is not a lot, you should always go for that. And it might sound very unsophisticated, but there's nothing wrong with that. So before we begin, I would like to tell something. So if you're running on different OSs, you might need to uncomment the name equals main block. Otherwise, it will give some freeze support error. So this is just how OSs function. And another thing is if you're using parallel processing, you might run into some problems, some bugs. Your code might get stuck somewhere and you have no idea what's going on. So one of the ways to monitor what's going on is you can use a system monitor, or like you can just a table of operations, which will tell you what process is consuming how much of your CPU. So you can actually gauge if your process is actually functioning or it has frozen because of like overusing your CPU or something. Yeah. So, and in Windows, I think you have a system monitor or something. So always keep a track on that. So now I'm going to tell you what multiprocessing.process is. So you use multiprocessing.process to do a specific task that you want to configure as per your niche requirement. So for example, here you have something like a matrix loop. And then your target is this matrix loop, and arguments is just something you pass into this particular matrix loop, your function, whatever it can be. And then you have a process list. And then you append each of the process to this process list. And then you start and join the process. So multiprocessing.process is a very customized way of doing things. So, and multiprocessing.pool is kind of a general way of doing things. So if you're ever unsure, just use multiprocessing.pools. And you can run it, and yeah, Colab is quite slow. Yep. And you can see that these are not in order, like it process 0, 1, 3, 4, 5, like, because they will finish as per they finish according to the core. It's not serially, it's like parallelly. So whatever finishes first, it'll output that result first. So, okay, now let's do a simple example. It is based on this particular multiprocessing.process code block. So let's say you have a Monte Carlo solver, which calculates a lithium decay. Again, let's not focus on the math, but this is like a general physics example that I wanted to bring on. So you have a decay function, which returns these particular things. And if you just do a simple plot, it'll look something like this. So now, if you want to perform this thing in like a serial decay. So what that means is you just have a for loop. You're running the entire simulation in series, so one after the other. And you have number of simulations here. You have already defined all the parameters, so like 100. And like, so if your PC is quite old, you can reduce this or increase it. So this is just an example to show you how parallel processing can speed up things. So if you do things in series, I'm quite skeptical of Colab. So you can run this right now on your, okay. So it took 9.38 seconds, whatever. And the same thing for parallel. So what I'm going to do is I'm going to give you like 5 minutes, and I'm going to let you fill this particular code block. And it's basically based on this particular example that we had here, multiprocessing.process. So you just have a target function, and you define the arguments, and then p.start, p.join. I've basically provided the skeleton here. So what you need to do, I'll give you 5 minutes to go through it. Let me know if you face any problem. Yes, someone.
I'm getting some errors and tracebacks when I'm running the code that you gave us. I don't know if anyone else is.
I am as well.
Yeah. Which one?
If you run it in Colab, it works.
Honestly, anything.
Oh, so it has to be running Colab.
Well, I don't know. It wasn't working on my computer.
Exactly.
Mine worked.
Can you tell me what?
Yeah. They did. But I did get this was Astro. No, you're not.
This one, right?
I get both.
Yes.
I get both.
It says everything's up to date when it's clearly not up to date.
So you have
I've done it on my terminal, but also here, you're supposed to be able to refresh it. And it will have all the new stuff in there, it does not.
Okay.
keyboard interrupt.
Well, yeah, because
It was taking a long time.
yeah, and it just output this immediately. So I thought,
Verified by more. But I didn't make this.
see the one.
Okay.
Yes. Does it, I need help.
So the first.
Figured you seem helpful. I'm just really struggling with, I can't get, like, I've been pulling on my terminal and it says everything is up to date. And even refreshing even on VS Code, but this is not the current version that is on
Yeah,
GitHub.
that's.
Looks like the latest thing in your graph is 125 weeks, and I have
Yeah.
1,000.
Okay, let's take last year. So you guys are facing problems here, right?
Let's work on collab.
Okay,
It
just work.
says everything is already up to date. And
Yeah, I'm not sure, so. If I
like
do it
everything is
here,
where.
just import and stuff, it works.
Okay, I will do that to make just for now for the last time I can share with you. Wait. Stuff like that. You know what this is? For me.
yes.
Okay, I'll go to the other one. Go to the other one.
That's what my
I mean,
advisor
I've
is.
used processing before on my computer
Yeah, I'm not
pretty
sure.
frequently.
So what did you do?
This is the school.
Look what happened?
Yeah, maybe you can,
I had it.
or you can just
different.
try to run the LIDK, it's the same code. So if nothing is working for you guys, you can just run the LIDK.py files that I have. One is for normal, one is for series, and the parallel one is the one that you can edit and fill.
Oh,
Okay, so this. Okay, so this was for serial decay. So what you do for parallel decay is just you start recording the time.
Sorry,
And-
you increase the size?
Yeah, sorry. Okay, is this okay?
No.
Is this okay?
Maybe another one?
Is this okay?
Try posing your terminal on your
The
sidebar.
file panel. Then you can use that.
And different. Okay, that's perfect.
Okay. So, yeah, so for parallel decay, you just define your entire array of processes, which is mp.process. Your target worker was already defined here, and it takes in all these arguments. So just give random seed, and then the same arguments, and then iterate it over all of the simulations. So that's the basic way of initializing all of your processes in this processes array. And then, of course, you need to start and then join. And then you just plot. And it should be super fast. Like, since I'm running this on my local, it's like 0.39. And whereas this one took 3.93 to 8 seconds. So parallelism definitely speeds up things. Yep.
I'm confused on where you said in the function worker, why you said complete the function. Is there something we are missing there? Like, was that all it was? Is those 3 lines?
I think that.
I think we have to write the decay of particles, right?
Oh, yeah, of course. So here, the metropolis decay. Yeah, I think I forgot. So
Wait.
yeah, there's the decay function there.
Okay.
Yeah, and that should be fine. And yeah, I think we can get rid of it. Now, if we come to pools, so multi-threading is a bit finicky, especially because you need to define your process very specifically. Like you need to exactly define your worker process and your arguments and everything. But if you're ever in doubt how to use, just use multiprocessing.pools, because there you can just define the number of worker processes that you need to spawn based on your number of cores. And then you just send all of your processes and they will be run on those different cores at the same time. For example, there's a function called matrix pool, so which does some function on some matrix. And this is synchronous parallelization, so which is just, you have basically just a for loop. And so essentially what matrix pool is doing, so in order to keep a track, you can see that this is printing job 0 complete, job 1 complete based on the index. And you're calling this matrix pool within your pool.apply. So if you execute this using the pool.apply, pool.close, pool.join, you can see that it's doing something weird, job 0 complete, job 1 complete, and randomly, as per the jobs are completed and created, it's just printing it out, and then it's printing all the results simultaneously, one after the other. So the way this functions is that once you go into the matrix pool, it'll initialize all of your processes. So based on what completes first and what is created, it'll print all the statements accordingly. And after that, it'll enumerate over the entire output set. But if you do asynchronous parallelization, which is used by, whose syntax is pool.apply async, and then you do the same thing. And here, again, you close the pool, you join the pool. You see that first all of the jobs are created. And then as per like what is completed first, it is displayed. So you can track that by these print statements. So these are the two different ways of using multiprocessing.pools, like async and normal apply.
I have a question.
Yeah.
Is there a specific use case for like one versus another?
Not really. So the basic idea is that both of these are parallelism applications, but synchronous parallelization is like it'll wait for all the process to upload, and then once all of them are done, it'll give you out the result altogether. Whereas in asynchronous, it'll just like keep doing as it is done. Like it'll keep printing out results as they are done.
Sure.
So there can be some functions where you have to wait for all the process to be done processing and then do some particular thing.
Okay.
In that case, you might go for synchronous. But if you don't care about like the order in which the things are done, you can just do async.
Right.
But was that your question?
Yeah.
Okay. Cool. So this is synchronous and asynchronous parallelization. So now I'll briefly tell you about the two different libraries that we use for multiprocessing. So one of them is OpenMP, which basically uses all the different cores, and all these different cores share the same memory. So what this does is you can always load something up in your memory, and all of the cores can now access this particular whatever you have initialized in your memory. So whereas this other library called MPI, it has a different memory associated with each of the cores. So one downside of this is that all of your cores need to communicate with each other. So if a parallel task is being processed on all 4 of these cores simultaneously and one of them finishes, it needs to let everyone know that, hey, I have finished my task. What's the status of your task? So you need to kind of broadcast everything. So now you might think that OpenMP is obviously a very good choice. Like, why don't we go for this? Because all of the cores just share the same memory and they're doing the same thing. So the reason for that is something called as the GIL, or the global interpreter lock, which is basically a restriction in Python. And it makes sure that only one thread is able to run a particular Python process at any given time. So which sounds like a bad idea, but this exists because there is a very large overhead that the threads communicating with each other. If a same process is going on two threads, the communication becomes very complicated in Python, so they did not want to go through that. So they just said, okay, what we're going to do is we're just going to let one single process run on one thread at one particular time. And that's the global interpreter lock. So because of this restriction, you cannot really use OpenMP in Python, but there are some workarounds using CPython or but this works in like C, Fortran, and everything else. And this is one of the main frameworks of parallel processing. But since we're going to focus on Python, so I'm just gonna, you can try to go through the C code in your own time. So we'll just focus on the MPI, which we can implement in Python. So it's kind of a standard library for parallel computing in Python. So this is kind of like the hello world program in MPI. So you just initialize your MPI world, and then the communicator size is basically the number of cores that you're using. And the rank is just like the ID of all those cores. So if you have like 4 cores, the ranks will be like 0, 1, 2, 3, 4, or 0, 1, 2, 3. And it'll just print out what your host name is, the rank, and like a basic hello world program. So I have a small task for you. So you can go through this nbody.py code, which is an implementation of OpenMPI. So it has a lot of mathy stuff, but I'll give you like a couple of minutes to go through the code, and then I'll try to explain the parallel processing aspect of this particular code. So it should be there in your repository right here. I'll give you like a couple of minutes to just go through the code. It's a bit mathy, but let's try to focus on the parallel processing part of this particular Py file. I think some people are unable to pull stuff from GitHub, and it's so unfortunate that it's some issue with GitHub apparently. So yeah.
We just have to wait.
Yeah.
The servers are running again.
Such an unfortunate timing.
Yeah.
Code Astro. Okay, so to briefly explain you like the parallel processing part of this particular code. So for this, to use anything MPI related, you need to install the MPI 4Py library. So you can just pip install MPI 4Py. And the way you initialize your environment is by just saying MPI com world. That's how you initialize in MPI. And then you have this particular position velocity, and you calculate it using this particular function. And now after you do any calculation, what you need to do is you need to broadcast your position and velocity to all of your entire world, basically. So com.bcast just lets everybody know that, okay, I have calculated, and now my updated position velocity is this. And in your main function, you will just you can just get the total number of processes, rank. And so here you might wonder how exactly because I have not defined anything core specific, like I did not tell it how many cores I'm using. So the way you run the code is by doing something like this, MPI run. And here is where you specify the number of cores. So if you just say 1, the entirety of your code will just run on 1 core. If you say 4, the entirety of code will run on 4 cores. And by using the MPI.broadcast thing, you can just communicate with all of the different cores that, okay, I have updated, I have done some calculation, here's the new thing, and then you can go ahead from here. So if someone manages to run this, you can visualize like what happens with different cores by just updating this particular array, and it will give you like a plot. Now, in order to debug your code, MPI also has a debugger, but this is very nasty. It's like it spawns up very small, tiny windows, and the number of windows depend on your number of cores. So if you say you want to use 4 cores, it will spawn like 4 tiny windows where it's impossible to see anything. So it's a nightmare overall. So that's why we mainly focus on like not going into parallel processing unless it's absolutely essential and you're absolutely sure that it's going to save up a lot of your time. So yeah, just appreciating this amazing. You can always do all of these things, but then yeah, you can also just yeah. So coming back to like, do you really need parallelism? Depends a lot on your use case. If Python notebooks are going to do what you need to do, you should use them if there's not a lot of overhead. But if it speeds up your processing by a lot, by like a factor of 10, 100, then of course you should go for it. Another thing is GNU parallel. So instead of writing any scripts or anything, you already have like something which can parallelize things. So if you want to run, let's say, process.py and it takes like a FITS file and you use Python to run it, you can just like append parallel before it and specify like, oh, just do these process.py on all of my 100 files and it'll do that for you. So this is GNU parallel for you. And to recap, multiprocessing versus multi-threading. So there's something called as global interpreter lock, which I explained, which prevents Python to do kind of multi-threading processes because it only processes a single thread at any given time. And these are some key differences. So basically, threads all use the same shared memory, and processes use different memories for each of your process. And so processes are very isolated. If a single thread crash, like your entire thing can crash. So depending on your task, you might want to go for threads or processes. And yeah, this is you guys going to be like for your project. So for your project, I'm very sure none of you will require parallelization. But this is just in case you might require parallelization somewhere. You can refer to all these notes. I have included a bunch of stuff, bunch of resources. And finally, I'll give you like, here's an activity that you can do for like 20, 25 minutes. So I have created this particular function called like generate fake data, which just creates like a bunch of images. And then there's a function which is going to process all these images. So the way to process it is just like filter data. So this is just going to do like for a single image. So what your task is to write something that will be able to run all the images in parallel. And then you can play around with that. You can increase the number of processes. You can do whatever you want. You can use pools. You can use mp.process, mp.pool. And let me know on Piazza what the results are, and you can use your driver navigator system to do this particular activity. It's there in the parallelism.ipynb file. Yeah, and optionally you can make a graph of like how much time it took when you use a single processor versus multiple processors. And yeah, let me know. I'll leave you with this activity. Yep.
But GNU parallel, I got confused. When you do it for 100 files, does it like do it at the same time or one by one? It's like
no, parallel at the same time.
It's parallel.
Yep.
Like repeating.
Yep. No, it's not serialized. Yeah, it's parallel. So that's a cool GNU parallel trick.
And if I have files of different names in the same folder and I want to do it like this, like different names but all in the same folder, I want to do those parallel. Because we have file 0, 1, 2, 3, 4, like in a particular order, right?
Yeah, exactly.
File A, B, C, D, or different names.
You might be able to use some regex magic to do that. Or another alternative could be you can just rename all the files using another Python script and then
That is.
Yep.
What's, I don't think I'm understanding like the main functional difference between using multiprocessing versus MPI.
MPI is,
In Python, that's specifically.
yeah, multiprocessing is like,
These cases.
so if you import multiprocessing, it's just a module that you're importing to perform multiprocessing tasks like pool, mp.pool, mp.process. Whereas when you use MPI, it's like a completely different thing. I'm not sure what the functional differences are. In theory, it should do the same thing, but these are just different ways to achieve the same thing in Python. So
You can, yeah,
you can,
as you import MPI for Py.
Yep, exactly. So it's like a separate, different thing.
It is the case.
But functionally, I don't
Not
see
every
there should be.
So what's the difference between multiprocess and multiprocessing in terms of the Python modules? Because I know there's also one called multiprocess.
Yeah, I would actually. That's.
I think we just use multiprocessing for this particular lecture. I'm not sure what exactly the difference is.
Okay.
And then, yeah, another package with the same name, right? Multiprocess.
Yeah.
Almost, yeah. I don't know what, I think multiprocess was a package, it's like, I don't know, an official Python package.
Mhm.
They're just tagged on and multiprocessing. has-
Yeah. Could be. I mean, there are a lot of things doing almost the same thing.
Yeah,
So it's a bit,
Thing should be.
yeah.
I'm gonna be honest.
Yeah, so multiprocessing in general is like a very fiddly, finicky thing. It's a deep dark forest. Where debugging is impossible. So another good trick to debug stuff is, so if you have set up a multiprocessing script, and if you're using like 10 cores and something falls apart, something's not working and you're unable to debug, you can always set the number of cores as 1 and then try to figure out what is going on where things are breaking. And then you try to go to multiple. So that will save you some time.
I have a question about GNU parallelization. You need to have like a graphical device to do GNU parallelization, or you can use like your graphical cores of your
I
own
think
machine.
your own machine you can purchase it.
Okay,
Yeah.
so you don't need like a graphical.
Not really.
Or
If you have, you can use.
yeah, of course, but I can use my graphical cores.
I think so. Yeah.
Okay, nice.
But then if you're using GPU, you need to go into like the CUDA drivers, like all of those. An entirely different mess.
Yeah. And how was the leg? How was the leg that my machine do the parallelization using GPUs rather than the GPUs?
Yeah, no worries. Sorry?
How I decide what to use in my code with
Between
yeah, like how I use like how I say to the machine like use GNU rather than GPU.
oh, so for GNU, you can just give like parallel, like the command parallel is only in GNU. Yeah,
Okay.
exactly.
Oh, it is like the default.
Yeah, exactly.
Oh, okay. And multiprocessing is for GPUs.
Multiprocessing is for CPUs, like
GPUs.
yeah, the computing units. You can just you have a Python script, use import multiprocessing and then mp dot pool or like whatever you want. You can initialize and then it will use all the cores of your device or yeah, or your cluster or like
Okay.
whatever.
Okay, nice.
I think I got confused into what was multi-processing and multi-threading. Are they the same thing?
Yeah, no, it's a bit confusing, I agree. Yeah. So So multi-threading is just like you have the same process running on different threads. So all these threads, they share the same memory.
Okay.
It's like I have a process and then this outputs something that outputs something. Is that like a thread?
So a thread, so you can think of it this way. So you have, let's say, a single core, and if you want to run multi-threading, then, and you say, if you want to spawn 4 threads, then all these 4 threads will be spawned in the same core. So they will share the same memory. So
Okay.
4 different things will happen on 4 different threads in the same memory space.
Okay.
So that's how you can think of it. Whereas a process, it happens on a single core.
Okay.
And if you have 2 processes, that means 2 cores are running simultaneously to do things.
Okay.
Yeah.
Okay.
Alrighty. Hi everyone. I'm Al. I am one of the TAs for Code Astro this year, and it's about the top of the hour. So I want to give people an extra minute or two to come in because I know this is one of the optional sessions people might be coming from working with their groups. So in the meantime, I'll just make sure I'm sharing my screen correctly and whatnot, and make sure you guys can hear me okay. At least they're in the room. Okay. No one's yelling at me in the chat, so I'm gonna share my entire screen for reasons that I think will make sense eventually. Because I am not good at remembering stuff, and I just like to have code documentation open while I'm doing things. And that's an okay way to do it. So, we're going to be, for those of you who are here, we're going to be in the day of, it's in the day 1 folder because this was originally going to be a day 1 lesson, but I believe it's still there anyway. Yeah, and then this is the astropy.ipynb notebook. So assuming everybody can navigate to there, essentially this lesson will be us scrolling through this notebook together. There's going to be some code that I'll talk through, and there will be a couple of breaks for you guys to try stuff. And we'll see how it goes. So, yeah, we'll jump right in to Astropy. So what is Astropy? It is a Python package that offers tools and functions useful for various tasks in astronomy and astrophysics. There's a whole bunch of stuff that it does, and I think that this is a good lesson to introduce you to what are some of the most useful aspects of it, the things that at least I and a lot of the folks that I've worked with use really commonly. And also to emphasize that in order to make use of Astropy, like you don't have to know what every single sub package does. You don't have to have every module memorized. But there's a lot of tools here that will prevent you from having to like reinvent the wheel on how to do stuff like, coordinate transformations and dealing with units and et cetera, et cetera. So I've linked all of these blue things are links to the official Astropy documentation, which I'm also going to reference heavily in this lesson, in part to show how like it can be useful to just have these things open while you're coding. It's not cheating, it's just using the resources that are available to you. So some of the commonly used sub packages, and some of these we're going to talk through in more detail, are like the Astropy units, which handles like defining, converting between, and doing math with physical quantities. So a number associated with a physical unit, like some mass or length or whatever. There's a package of constants, which contain stuff like the gravitational constant, the Boltzmann constant, a bunch of like handy physics quantities, and astronomy quantities, the mass of the sun, the radius of Jupiter, stuff like that. Those are really handy to use. There is a table subpackage that creates a data structure. It's similar to Pandas tables or data frames if you're familiar with those. If not, that's fine. So we'll talk about that a little bit. There is a subpackage for reading and writing FITS files, which are a really commonly used data format in astronomy. There's stuff for like time when you have to convert between a literal calendar date versus like the Julian date or the modified Julian date. It knows all about all of those things. And similarly, coordinates, which are super messy to try to do by hand, especially like, converting between a location on the surface of Earth to a galactocentric location to, whatever. All that kind of stuff. But Astropy is a community developed package where a bunch of astronomers were like, here's a handy thing that we should have and be able to reference. So a lot of people have put like really good work into this, and we should use it if we know, that it's available. So you import Astropy just like you would import any other Python package. You could import all of Astropy just by saying import Astropy, and then you would have all of it. But that can take up a lot of memory. So ideally, when you want to use stuff from big packages like Astropy, NumPy, SciPy, stuff like that, the best practice is if you know exactly what specific tool you want to use from it, you can say from Astropy import the particular sub package, or even from Astropy dot that particular sub package import the particular class or function or whatever it is that you want. So those are options. So if we start just looking at like the units and constants sub packages, which kind of go together. The way that these work is they define a special data structure called a quantity. And you can think of it like a tuple of a float, just some number, combined with a unit like kilograms or seconds. And this makes it really easy to do math with different units. It knows how to, convert from kilograms to grams or from ergs to newtons, which is a lot harder than getting from kilograms to grams, and stuff like that. And so you can add things that have the same like dimension. So if you add one mass to another, it knows how to do that as long as they're both masses, even if they're different units. And if you multiply and divide stuff, then it can like create the compound units that you would expect, getting from like mass divided by a time, or rather a distance divided by a time gives you a velocity of some kind. So we can import the units and constants subpackages by running this cell. And now we have access to everything in these two subpackages. So the first thing I'll do is run this cell below, which basically shows you how you create a quantity. So the units, the way you access just a unit is by typing u dot whatever unit you want to use. And there's a table linked here that shows you. Oop, okay, it's automatically scrolling. I love that. These are all of the units that you can access via this package. It's got stuff for frequency, energy, temperature, a bunch of stuff I've never used. But whenever I can't remember like how specifically to type, if I want Kelvin, am I allowed to just write the letter K? Yeah, that's allowed. There are a couple of different ways to call each one, but this is a handy table just to have to reference. So if I wanted to create some distance to keep track of, I could do a float 15.1 times meters. And now this is a quantity that has both, the magnitude and the unit. Similarly for a time with the units of seconds. So if I print this, I'm printing a couple of things here. If I just print like the entire variable, it'll display this is the value and this is the unit together. But if you ever want, for whatever reason, just to pull out the value or the unit by itself, you can use that by accessing it via the attribute directly. So you can type d.value and that'll print out or return just 15.1. You can do d.unit and that'll return just the like meter unit. So as I mentioned, you can do math with these things, which is really handy. So if I wanted to get a velocity by dividing this distance by this time that we defined up here, when I do this, it will show, okay, now you have a new quantity and it has also updated the units associated with that. There are ways where like it'll do that automatically when you're combining, different quantities with different units. You can also manually convert one unit to another as long as, again, they have the same dimensions, as long as you're going from a velocity to a velocity. So say I wanted to convert this meters per second to AU per year, which by hand, I would have to double check a bunch of things to do this. But instead, I can use the .to method, where I basically say, okay, this quantity has some units. I want to convert it to this unit, where I've constructed my own compound unit by saying u.au divided by u.year is the new unit I want this to have. And so this is the result of that line, where it's just done all of the math for me, and I don't have to worry about it. This is like the variable. This is the thing that allows you to like make variables that have these units. But as I mentioned, they also have a bunch of pre-computed constants that are also quantities that also have the units associated with them directly. So if I run this cell, we will get the gravitational constant G. And if you just say print G, you actually get a few things. So it has the name of the constant. We refer to it as the gravitational constant. The value, which is what you would get if you said G dot value, it would print this. It also has the unit, which is some complicated unit that you don't really want to have to think about if you don't have to. It also has the uncertainty on that constant, which may or may not be relevant, and then a reference to where it got it from. So the gravitational constant I like as an option because there are it's one of these complicated units that's annoying to have to think about, but because Astropy can take care of a lot of that for you, it makes a good example of how to work with these. So now there's an opportunity for you guys to try working with these yourselves. And the task, which I'll give you about 10 minutes to do, is to calculate the gravitational force between a star with 3 solar masses and its planet of 10 Jupiter masses, which is 2 AU away. So you have the mass of the star, you have the mass of the planet, and you have the distance between the two objects. So can you, using these Astropy quantities and constants, calculate the gravitational force? Let's see. It might be handy for you to pull up just the like general units documentation, which shows you, just like we went through how to construct the objects and how to convert units and things. If you need help finding I don't want to ask Copilot anything. Finding the equation for the gravitational force, feel free to drop any questions in the chat. But that's a pretty Googleable equation. And yeah, with that, I will ask if you guys have any questions so far, and two, yeah, give you guys about 10 minutes to poke through this. Okie doke. Cool. I think this button will resume my screen sharing. Yeah. Gotcha. So, the solution that I came up with was to set up our individual variables of our star object, our planet object, and our distance. And then this being the equation for gravitational force. We got the constant g earlier, so we can just use that. If we run this code, then we'll get a result with a truly wild looking set of units. So this is because it just will combine all of the units together. And so then what we actually need to do is convert it to units. And so once we do that, we get 8-ish times 10 to the 25 newtons. So if that is, did we all get a similar result doing this? Okay, I'm seeing nodding. I love to see nodding. Cool. So that's just an intro. These are super useful if you want to make sure that you're keeping track of these things correctly and not having to trust your own comments that you're doing this. So there's a question online, shouldn't we convert the AU to meters? The beauty of using Astropy quantities is that it can do the calculation no matter what units you have. And then as long as your dimensions are correct, you can always convert to the unit that you want at the end. So you don't have to put it in with meters as long as you have initialized your quantity with the units that are correct for that float value. But it can always convert at the end. Is the end sun divine? So this is an alternative to soul mass. It means the same thing. If we go to this the table from before, I think we should be able to see. Boop, there are a few different ways that you can call each. So for example, for Tesla, you can use T or you can use the word spelled out. So M sun is the same as soul mass for this purpose. Yeah. Okay, so the next section is on Astropy tables. So again, these are really similar to NumPy, or rather to Pandas data frames, but they know about Astropy specific things like time and coordinates and quantities. So if we run this cell here, we're importing the table subpackage. We are setting up a couple of columns. So one of these is just an int, a column of integers. One of these is a column of floats. This is a column of strings, and this is a column of quantities. So you can take a list of floats or integers and multiply them by a unit to get a list of quantities. So when we put all of these into one table, we'll see that you get the name of each column that you set up, and then you also have the data type for that column. And then in between those two rows, if there's a quantity, then Astropy will know that there are units associated with a given column. So that's just a helpful thing to have. We're not going to go into that in too much detail. It's just nice to know. The thing that I think is particularly useful is learning more about FITS files, since they are a super common data format for sharing stuff in astronomy, and they can be a little bit opaque. So first we're gonna, from the Astropy IO, which stands for in out subpackage, we're gonna import the FITS sort of sub package, which is just all types of like reading, writing, editing FITS files, and we'll grab their included like test data FITS image. So now we have the file name for that object. And before we open it, I want to talk a little bit about what actually is a FITS file. So they are the reason they're useful is because rather than just say, I have this big array of data, I'm going to send it to my collaborator, have fun. It is a way to associate that data array of however many dimensions of numbers with metadata or information about the data. And so the most basic sort of structure is you will essentially have a header data unit where the data, oh, hello, The data is like, the array of numbers that you have. And the header you can think of as kind of a dictionary of keywords. But rather than just a Python dictionary, it's not just the keyword and the value. You can also add comments to describe what this keyword actually means. And so here's just an example. If you want to know, for things you would want to know if this is an image of a particular object, what the object is, what observatory or telescope it was observed with, what filter was used, what settings the observatory had, the date of the observation, all that kind of stuff is information that can go in the header associated with the data. And then those two things are sort of bound together in this HDU, this header data unit. So a FITS file can contain more than one HDU. So when you open up a FITS file, what you actually get is an HDU list, which is exactly what it sounds like. And that you can grab using the function fits.open and then your file path. And then what we'll do is call this .info method, which is just a handy if somebody has sent you a FITS file and you're like, I have no idea what's in here, I don't know where to start, you just do hdul.info. It'll tell you a summary of what's in the file. So we have 5 objects in our HDU list. There's the primary HDU, which typically is just a header and actually has no data associated with it. It's just like the highest level background information that you would want to know about the data. And then you might have additional data files that have images or data cubes in the data. So what each of these columns basically tells you is the type of HDU it is. The cards is like, this is the number of key value pairs in the header. The dimensions tells you the dimension of the data array itself. So you can see there's no data actually in the primary HDU, but then there are 4 images, which are each 40 by 40 pixels. And then it'll tell you the data type. So in this case, it's int16, which is a type of integer. So how to actually get to the data, because if we say just display or print HDUL, we just get, oh, this is a list of images, but it doesn't really know what to do with that yet. So instead, we'll say HDUL 0, which will get us this primary header, or this primary HDU. And then we'll say just display the header. And that, or you could do print, but display in Python notebooks tends to be a little bit more readable. So this will actually give us each of those key value pairs and the comment that tells us what the key value pair is really representing. So, the date the FITS file was generated, stuff like the filter configurations for the observations, the instrument status, all kinds of things that, you might want to know about the data. Then we can say, okay, well, let's look at this actual image. And to get to the actual data array, then you'll say, okay, HDUL1 will give us this first HDU in the FITS file. And then .data will take us to that actual data array. So this gives us basically a NumPy array of integers as expected, with a shape 4040. And we can always say like plt.imshow this this image. Of course, I'll have to import matplotlib. And now we can actually look at it, and it's not very interesting, but this is just an example. So generally, when you open a file, you do always want to remember to close it when you're done with it. So we'll run this hdul.close function to get that file closed. And now if I were to try to access anything in this HDUL object, I think in this case it still works. I've run into things where I close the object and then I try to access the data in it and it does weird things, but I guess it's working right now. So we love that. So hopefully the concept of a FITS file and what's actually going on inside this is a little bit less opaque. But you can always, again, like just check out the documentation if things are confusing, and poke through here to see what's going on more under the hood, because I do that all the time. Yeah, the final thing I wanted to talk about is maybe more a more specific practical situation, which maybe you are an observational astronomer trying to actually plan an observation. And so in order to convince an observatory to let you look at an object, you need to prove that, well, you know when that object is going to be in the sky, you know it's not going to be too close to the moon, you know you'll actually be able to do the observation. So the first thing we're going to do, because the package Astro plan, which we will use for this, is not included in our like original setup instructions. What I'll have you do if you haven't already is uncomment this line and actually run pip install Astro plan. And that'll make sure that you have Astro. I've already installed this, but you should get a slightly different but correct message that you can add Astroplan to your environment. And then what we'll do is check out the docs for astropy.coordinates, and for Astroplan's observer. So these are the tools you're going to need to use. And I've left some structure here so you kind of have an idea of where we're going. But to just quickly pop over to the coordinates for Astropy, essentially they have you can think of it a little bit similar to units, where you have values associated with particular units with a particular reference frame. So in this case, this sky coordinate object has been defined in the ICRS reference frame, but then you could translate that to other reference frames. So what you guys will want to do here is try to plan an observation of Fomalhaut from the Subaru Observatory. So you will need to find a way to look up the coordinates of a particular object. There are ways to do that by name, which you'll find in here somewhere. And then using the, I believe, yeah, you can also find the locations of particular observatories through the observer object in Astroplan, and then convert that to a coordinate location. I realize I've given you very little exact info on how to do this, but part of that is because I want you guys to have experience like, okay, we know we want to find the coordinates of this object. Can I read the documentation to get a sense of how to do this and come up with something? So I think another 10 minutes or so I will check in, but I will let you sort of peruse through these two documentation pages I've listed and linked in the text up here, and note that for this code block, these are the classes you'll want to use for this. So yeah, any questions so far? Otherwise, I'll let you start poking around.
Yeah, is anyone else having issues with installing Astroplan?
Yep.
Yeah.
Okay, awesome. Love to hear it. Is it giving you like a dependency error?
It's saying it's an issue with the package mentioned, not pip.
Fascinating.
38 lines of output, did not run successfully, lots of traceback errors. There's a key error, subtool, setup tools _SCM.
Gotcha. Okay. Well, in that case, let's ignore the astroplan aspect of things. Focus on just getting the coordinates for Fomalhaut, and I will see if there's a way to do this using just Astropy. So I'll check back in a few minutes. But for now, you can find the coordinates of Fomalhaut with just Astropy. Awesome. Hello, it's Elle again. So yeah, if you're able to get Astroplan installed, that's great. You also, I figured out, you don't need it. So there is the Earth location class has a list of observatories as well. And so you can, and yeah, there's info on how to find the Earth location of particular sites also in there. So you can, I think you can do everything just with Astropy. Yeah, I'll give you a few more minutes to keep poking around in here, maybe about 3 more minutes. And then we'll talk about solutions. Okie doke. All right. So, the solution that I ended up with was to use okay. So in this reference document on the left, there are a few convenience functions that they call out. Let's see. And one of them is this from name method of SkyCoord. And so this allows you to say, I want the location of a particular object, and then it will return that in a particular reference frame in RA index. And there is a similar one for observatory. Yeah, for observatories to find their Earth locations. So you can do Earth location.ofsite and then the name of the observatory. And you can also, there's a method get site names, which will just give you the entire list of all of the observatory sites that are saved already in this module. So what this gives us is the coordinates of Fomalhaut in degrees, RA and DEC, and then also the geocentric coordinates of the Subaru Observatory, which are in meters. If we want to know more about why that is the case, I believe these are geocentric coordinates. And so it's really like meters in XYZ from the position of the center of the Earth. You can convert it to geodetic if you would like to, but we don't need to do that yet. This does include like altitude information, which is good. And so what we'll do, the overall goal essentially is to make a plot of where is from the position of the Subaru Observatory, where's the position of Fomalhaut in the sky over time, and where's the position of the sun in the sky over time. So we will run this cell as is. This imports the time sub package from Astropy. And so what we're going to do is define midnight as, time 0 on the date of the observation, say July 31st last year. Then we'll say we want to define a grid of times between 12 hours before midnight and 12 hours after midnight. So this is a numpy.lin space giving us 1,000 points between -12 and +12. And then we're multiplying this whole thing by the hours unit. So because we have this Astropy time object and this Astropy quantity that is a unit of hours, we can add them together to get the times from noon before the night of the observation to noon after the night of the observation. And then what we can do is convert things to the altitude and azimuth reference frame. So this will convert our this will set up a reference frame so that at a given time and from a particular location, we know the altitude and azimuth of the sun and the stars as they should be as viewed from that location at that time. So this is how we will convert the Fomalhaut coordinates that we got earlier. We can use the dot transform to this new frame that we've set up, which is the more useful frame for planning an observation. So now the question is, so we'll just run this. So we have these variables set up. The question is, can we see the source at night? Will the sun be up, etc. So we can use the getSun function from astropy.coordinates. And what I think in the interest of time, maybe we can just walk through how to do this. So we have this getSun function that we now have access to. We'll set up some plotting things in the next cell, but what we really need is to know the altitude and azimuth of the sun at these various times. And the way to do that is we're going to grab the location of the sun at these times, and then that'll give us a general coordinates object, and then we will convert those coordinates to the altitude azimuth frame. So I'm just going to go ahead and copy this guy over here. Boop. And now that we have this, we can plot the altitude and the azimuth of the sun and of Fomalhaut over time. So I'm going to grab, let's see, this line of code, and I believe this one we need also. Yep, so just to walk through in detail what this is doing. plt.plot is your classic, I'm going to draw a line with various x and y coordinates. And so our x coordinates are the just the hours, like how far before or after midnight we are. So that's why we're using this delta midnight variable and just converting it to hours. And then just taking the value. So when you hand quantities to Matplotlib, it really just wants an integer. It does not know what to do with a quantity because it is not part of Astropy. So this is the case where you would want to say, I'm just taking the value. I don't care about the unit. I've already made sure it's in the unit that I want it to be. So I know the value will be correct. And then for this sun, altitude, and azimuth, we're going to take just the altitude and plot that as our y value associated with each hour. So similarly, we'll do the same thing for Fomalhaut, just using the Fomalhaut variable. And then we're adding a color map to show the azimuth. So that's the, what cardinal direction in the sky you're facing. And then altitude is just how high above the horizon are you. There's a bunch of other stuff to make some nice details happen here. So when we run this, we should get a few things that we're looking at. So this blue line shows us the position of the sun. It goes up and then it comes down. Great. The colored line shows us the position of Fomalhaut. So we can see in this darker region of the plot where the sun is below the horizon, we have Fomalhaut high-ish in the sky at 40 degrees. And so then this azimuth tells us what direction in the sky it will actually be. That's important for some observatories, whether you'll be able to face in particular directions at particular times. So if you wanted to, you could also add the moon to this plot, and maybe place restrictions on how far away the moon has to be from your target in order for you to look at it and actually get good data, stuff like that. There's, yeah, additional, this was mostly based on this Astropy lecture, which has some additional details in it by Phil Udley. So if you have like further things you want to check out, feel free to look at that link as well. I've tried to include as many links to like handy references in this so that you can come back to it as a reference. But hopefully this has just been a good like sampler platter of the things that Astropy contains, some of which you might find more useful than others. But hopefully there's something in here that's like, oh, nice. That is a tool that I will use and will make my life easier in some way. So yeah, we have a few minutes left for if y'all have any questions, or if anything was particularly confusing, feel free to let me know.
Oh, why is it showing the sun as high in the sky around midnight?
You know, that's a really good question.
That can't be right?
Yeah, that really actually can't be right.
Well, it's from UT midnight. Also, the shape of the sun, like path, doesn't really make a lot of sense either. That it would just like sharply change altitudes like that.
Yeah. So okay, the point about it being UT midnight is a good point. So UT midnight is not the same as
I see.
the midnight locally at Subaru. Necessarily. Yeah. The shape is a bit weird. It should be, in my mind, more sinusoidal. And that, yeah, that's something that I should ask about.
Maybe we could use the scale because you like 13 hours of sun, which is most normal.
GPS signal lost.
Mm-hmm.
Where am I going?
Yeah, that is curious. And I will look into that and make sure that it is correct for next year. I think.
Cool.
Yeah, I'll figure out what's going on there.
Okay. Just one.
Okay, anything else in the last 2 minutes? If not, thanks for coming to this optional session. I hope you learned at least one useful thing. I will be around on the Discord and the Piazza for the rest of the week. So yeah, if anything comes up that you wanted to ask about, feel free to reach out.
Thank you.
Thank you.
Sure. All right. Enjoy the rest of your day.